started with just ask everybody to maybe mute their microphone if they're not asking a question. Okay, so it looks like you have them up there and you're ready to go, Edward?
Okay, I apologize for the delay, but maybe we can get started now.
Yeah, please.
I also apologize to any of you who may have heard a similar talk previously. If so, this won't add much. So in this talk, I'm going to be explaining work with Davide Gaiotto, in which we try to understand in terms of quantum field theory, a picture that was developed by Eddinghoff, Frankel, and Kajan of an analytic approach to geometric Langlands for complex curves. And there were a number of early developments, which I'm mostly not qualified to summarize, so I won't try to. The one most related to physics was by Teschner in this paper. So in the first half of the talk, I'm going to review the gauge theory approach to geometric Langlands, because I don't want to assume you're too familiar with it. And then in the second half of the talk, I'll explain what we did to make contact with Eddinghoff, Frankel, and Kajan. So in the gauge theory approach, the starting point for geometric Langlands is what's called n=4 super-Yang-Mills theory in 4 dimensions with the gauge group G, or with the Langlands GNO dual group G dual. The theory based on G has what's called a gauge coupling constant and a topological angle theta, which combine to a complex parameter which is in the upper half plane since E squared is positive. So im tau is positive. There's an elementary symmetry of shifting tau by 1, which comes from the fact that instanton number is an integer. So increasing this angle by 2 pi doesn't matter. And likewise, the dual theory has an analogous parameter, tau dual, also with an elementary symmetry. The claim of electric-magnetic duality, which goes back to Montonen and Olive, is that the theories based on the dual pair of groups are equivalent under this transformation that exchanges tau with -1 over tau for simply laced groups, and then there's a 2 or 3 for other simply groups. Now, this isn't a statement about geometric Langlands. Geometric Langlands is highly asymmetrical between G and G dual. Not just geometric Langlands, but number theory Langlands is highly asymmetrical. However, here the statement is completely symmetrical between the group and the dual group. The asymmetry arises because of specializing to particular questions. But before I get there, I'll just say, it's not particularly a statement about geometric Langlands. This duality is studied extensively by physicists from many different points of view, and they're usually studying questions that are pretty distant from geometric Langlands. But you can specialize to the situation that leads to geometric Langlands, and that involves breaking the symmetry between the group and the dual group. So first you consider a topological twist that leads to a CP1 family of topological field theories, parameterized by complex parameters psi or psi dual. If you study the whole family, the equivalence under psi dual equals -1 over n times psi becomes, along with these more elementary symmetries here, becomes the duality of quantum geometric Langlands in the language used by people studying that subject. But today we'll consider the basic geometric Langlands duality that relates psi = 0 for G, which I'll call the A model, and psi dual equals infinity for G dual, which I'll call the B model. In general, quantum field theory in dimension D associates a number to a D manifold, a vector space of physical states to a D-1 manifold, and a category of boundary conditions to a D-2 manifold. In the present context, we'll keep an oriented 2-manifold C fixed, so we only consider 4 manifolds of the form C times some other 2-manifold sigma. So everything depends on C, and in particular, we define a category of boundary conditions that depends on C. So it's convenient to draw 2-dimensional pictures in which you only show sigma. If sigma has a boundary, then to formulate quantum field theory on sigma, you need a boundary condition. So I've sort of symbolically drawn here a 2-manifold with a boundary, showing only the local behavior near a boundary. Boundary conditions make a category. Given 2 boundary conditions, B1 and B2, Hom from B1 to B2 is the vector space the quantum field theory assigns to this picture, where we now have a more global picture. There's now a compact 1-manifold stretching between the 2 sides, ending on the 2 boundaries B1 and B2. To a 1-manifold, the quantum field theory, well, we're thinking of it as a 2-dimensional quantum field theory because 2 dimensions are kept fixed. So to a codimension 1-manifold is a better way to say it. This compact 1-manifold. a quantum field theory assigns a vector space that we think of as Hom between the two boundary conditions. And then Hom from B to B becomes an algebra for every B, because you can take a strip representing an element of Hom from B to B. In this picture, I'm imagining all boundaries are labeled by the same boundary condition B. Then you can take two elements of Hom from B to B, and this picture will combine them to a single element, giving you an algebra structure of Hom from B to B. And similar pictures show that Hom from B to B prime is a left module for Hom from B prime to B prime, and so on. So to explain this properly, I should draw some more pictures that I haven't included in these slides. So electromagnetic duality will give an isomorphism between the category associated to C in the G theory at psi equals 0 and the category associated to C in the G-dual theory at psi dual equals infinity. In addition, there's a natural mapping between certain natural functors on C and C-dual. These functors come from what physicists call line operators. So in a quantum field theory defined on a manifold M, a line operator is some sort of modification of the definition of the theory along an embedded one manifold, K. So the natural line operators at psi equals infinity are what physicists call Wilson operators. A Wilson operator is the holonomy of a connection interpreted as an operator in quantum field theory. We'll do it in detail in a special case later. And at psi equals infinity, at psi equals 0, the natural line operators are Hooft operators, which mathematically correspond to Hecke functors. In physics, Wilson and Hooft operators are usually used in studying physics problems like quark confinement in atomic nuclei, as well as other problems. But for today, a line operator is a functor from the category of boundary conditions to itself. We can understand that statement from this picture. So first, let's look at part A of the picture. Part A, we have a two manifold with a boundary labeled by B, but a line operator T runs parallel to the boundary. And in topological field theory, the distance between T and B is not defined. You could think of it as taking it to 0. So the composite of T and B just forms a new boundary condition that I call TB. That's the action of B on objects in the category of boundary conditions. For its action on morphisms, I've drawn another picture. In this picture in B, a morphism, see, I have a boundary which I have divided piecewise between portions labeled by boundary conditions B, B prime, and B double prime. And in that picture, a morphism is represented by one of these black dots in which the boundary condition jumps. The picture is conformally equivalent to another picture. So here, a morphism was labeled by a strip that goes off to infinity. But conformally, you could map it. You could sort of map it to this second picture, where the strip that goes off to infinity has been projected to a finite distance, and infinity on the strip is just a point where the boundary condition jumps. So in this picture, a morphism is the boundary is labeled piecewise by different boundary conditions. For example, it might be Dirichlet here, Neumann here, and something else up here. And morphisms between boundary conditions are just ways that the boundary condition can jump. Now, as T approaches the boundary, piecewise we have composite boundary conditions, TB, TB prime, and TB double prime. They're jumping. And the compositions of the jumps obey whatever laws they did before we brought T to the boundary. So T acts as a functor. So T obeys the right axioms vis-a-vis morphisms in the category so that it's a functor on the category of boundary conditions. Now, I've been drawing pictures in 2 dimensions, but there are 2 more dimensions not drawn, and T really depends on the choice of a point in the 2 manifold C. So such pictures make it obvious that the line operators T of P prime, and so on commute. So in a purely 2-dimensional picture, see, in 2 dimensions, the picture shows that we have a boundary condition B, not labeled here. We act on it with T of P, and then we act on it with T of P prime. And in general, these functors would not commute. In 2-dimensional field theory, functors on boundary conditions in general don't commute. But because there are 2 hidden dimensions, we can move the 2 line operators through each other with no singularity. So in this situation, the functors associated to boundary conditions commute. So the 2 dual categories, C and C dual, are equipped with dual families of functors parameterized by the choice of a point in C and some other data, and commuting at distinct points. So T of P corresponds to the usual Hecke functors of geometric Langlands, while W of P is its dual in the usual statement of geometric Langlands duality. W of P is more elementary, so it's not always stated explicitly as a functor on boundary conditions or on objects in the category. Since these functors depend on more data, namely a representation of G dual, you can also consider the composition of Hecke functors at the same point but associated to possibly different representations. And again, you can see they commute. Now, the duality says the algebra of compositions of Hecke operators should be the same as the corresponding algebra of composition of Wilson operators, but that on elementary grounds is just the tensor algebra of representations of the dual group. So this equivalence between the algebra of compositions of Hecke operators and Wilson operators mathematically is called the geometric Satake correspondence. Now, to go into a little more detail, I want to introduce a useful language to formulate a simplified version of geometric Langlands duality. So let M sub H be the moduli space of Higgs bundles, where I might specify the group G or the two manifold C. So as shown by Hitchin, this is a hyperkähler manifold. In one complex structure, which Hitchin called I, it parameterizes Higgs bundles. In another complex structure, J, it parameterizes flat bundles with structure group, the complex Lie group. IJ and IJ, which I'll call K, act as the usual unit quaternions. And there are also corresponding Kähler forms. So geometric Langlands duality, for many purposes, can be understood as a mirror symmetry between the A model of the Higgs bundle moduli space of G, viewed as a real symplectic manifold with a symplectic structure omega K, and the B model of the Higgs bundle moduli space in complex structure J. This instance of mirror symmetry is particularly nice because it's a rare case in which the Strometer-Yale-Zaslow picture can be made explicit. It was first studied mathematically by Halsall and Thaddeus. Now, you can definitely ask questions for which the two-dimensional picture is inadequate. Mathematicians describe this by saying that the theory should be formulated on the stack of G bundles, bun G, not on a finite dimensional moduli space. A physicist's way to describe the same thing is to say that the correct formulation is a duality of four-dimensional theories, not two-dimensional theories. 4 is the minimum. There's a description in 6 dimensions that explains some things better, but we won't go that way today. The two formulations are not as different as you may think, because Atiyah and Bott showed in 1981 that a model of bun G is the space of all connections on this fixed smooth G bundle over C. So a model of the stack of bundles on C is the space of all connections on a smooth G bundle over C. So four-dimensional gauge theory is a two-dimensional theory with target bun G. In other words, if you gave a physicist the question, what's a two-dimensional target with theory with target bun G, one might be baffled. But if one's given the Atiyah-Bott description of what's meant by bun G, then you'd realize that a two-dimensional theory with target bun G is actually just a four-dimensional gauge theory. Now, I want to use the two-dimensional description of geometric Langlands duality as mirror symmetry to explain why the category that appears on one side of the duality is a category of D modules on bun G. The most familiar branes in the A model or Fukaya category of a real symplectic manifold Y are Lagrangian branes supported on a Lagrangian manifold L. But Kapustin and Orlov discovered that in general one can also define coisotropic A branes that are supported on a coisotropic submanifold R above the middle dimension. The construction of coisotropic branes is delicate in general, but the simplest case is the case relevant to geometric Langlands. That's the case that Y, where we're doing the A model or Fukaya category, is actually a complex symplectic manifold with a complex structure I and a homomorphic symplectic structure capital omega. But one views Y as a real symplectic manifold, taking the imaginary part of omega as its real symplectic form. And then one takes the B field to be the real part of omega. Originally, Kapustin and I described this in a different way, related to this by a B field gauge transformation. With this data, you can construct what we call a canonical coisotropic A brane, BCC, whose support is all of y.
Edward, may I ask a question just because I'm a mathematician? So you're talking physics now, yeah? When you say the delicate construction, you mean like physics? There is no mathematical construction of...
Well, there can't be, because you'd have to understand the sigma model where Kapustin and Orlov were working. So Kapustin and Orlov deduced from the sigma model. Well, they deduced from mirror symmetry that these branes had to exist. And then they found them using standard properties of the sigma model. They arrived at this definition.
So what's mathematical construction except of kind of explicit realization as some d modules and so on?
Well, that's like asking what is mirror symmetry. Physicists work with framework that predicted mirror symmetry, but mathematicians have difficulty.
Okay, so that's physics. Okay.
It's analogous to that, right? So, in a clear framework, okay, from what physicists regard as the underlying definition, Kapustin and Orlov deduced this answer. But mathematicians, not having the sigma model available, tend to think of this answer as a definition. But to a physicist, it's an answer to a question that was asked about the sigma model. So with this data, they construct a canonical quasitropic A brane whose support is all of y. It has the property that roughly Ham from BCC to itself is related to deformation quantization of the algebra of holomorphic functions on y. So that's general, but this more specific case that will suffice for today is that if y is a cotangent bundle of some other complex manifold, then Ham from BCC to itself is the sheaf of holomorphic differential operators on W, acting on the square root of the canonical bundle of W. So if we want to do geometric Langlands, we take Y to be the Higgs bundle moduli space, which is birational to a cotangent bundle of the moduli space of semi-stable holomorphic G bundles on C. So then A, the algebra Ham from BCC to itself, is the sheaf of holomorphic differential operators on the ordinary moduli space. Then if B is any other brane, Ham from B to BCC is going to be a module for Ham from BCC to itself. In other words, the category on the automorphic side of the geometric Langlands duality is a category of, roughly speaking, D modules on M of G. Mathematically, you want to work with D modules on the stack bun-G, not on a finite dimensional moduli space. Physically, what that means is that it's important that a version of this brane BCC can be defined directly in 4 dimensions, not only after reducing to 2 dimensions. I reduced to 2 dimensions because then I could give the Kapustin-Orlov explanation, which is perhaps better known. But it was important to have a 4-dimensional version. And Kapustin and I had a version of that in our original paper. Gaiotto and I found an improved version a few years later. That enabled us to answer a question that had been, whose answer was well known to mathematicians, but had been not very clear from a physical point of view. What's the dual to BCC? So BCC is an A brane of the Higgs bundle moduli space, so its dual will be a B brane of the dual group. In other words, a coherent sheaf, or maybe a complex of coherent sheaves, on Hitchin's moduli space of the dual group in complex structure J. Well, Branes and Drinfeld had already shown what was the right sheaf. The D module corresponding to BCC itself is the sheaf of differential operators on M of G, the moduli space for G. Its dual is the structure sheaf of the variety of opairs, which is opers, a very special Lagrangian submanifold of the dual Higgs bundle moduli space. I won't explain right now what an opar is. We'll get back to that at the end of the talk. A gauge theory explanation of this observation of Branes and Drinfeld had been unclear, at least initially. But in this paper, we arrived at one. So in summary, here are the main ideas of the gauge theory geometric Langlands correspondence. There's electric magnetic duality between G and G dual for supersymmetric gauge theory in 4 dimensions. Twist to make a dual pair of topological field theories. Compactify to 2 dimensions on a Riemann surface C to get a 2-dimensional theory that depends on the choice of C. The dual theories have dual sets of line operators, including 't Hooft operators that are related to geometric Hecke transformations. On one side of the duality, there's this distinguished brane BCC, that establishes a map from A branes to D modules. On the other side, one is studying B branes on the Higgs bundle moduli space in the complex structure in which it parameterizes flat bundles. So I'm sorry I've rushed through this, but that's kind of necessary in order to be able to get to the more recent developments. What I've said so far involves deformation, not quantization. So I want to spend a moment to underline the difference, and I'll give the concrete example of a two-sphere viewed as a symplectic manifold with its usual rotation invariant symplectic form. So this is a real two-sphere. X, Y, and Z are real variables. This is a real symplectic manifold, which you could think of as the phase space of a rotating body, well, roughly, the phase space of a rigid rotator in 3 dimensions. It's a rigid body that has 2 vanishing moments of inertia, only one non-zero moment of inertia. Unless I got that backwards, but let me not straighten out right now. In deformation quantization, you'd start with the commutative algebra of functions, for example, polynomial functions in X, Y, and Z, or maybe smooth functions, and try to deform it to a non-commutative algebra. In general, you specify that the leading non-commutative deformation should agree with the Poisson bracket, and then you try to make a family of associative algebras over a ring C of H bar, or maybe a formal power series ring C double bracket of H bar with that property. Now, in the present case, you don't really need general theory. You can just write down an answer that's given by the SU2 Lie algebra with the relations I've written. That makes sense, together with a version of this relation, which I'll write in a second. That makes sense for any value of J squared and is not quantization. So quantization means finding a Hilbert space H of the appropriate size that the algebra acts on. So appropriate size in particular means that it's supposed to be a finite dimensional Hilbert space. And asymptotically, its dimension should be the area of the phase space divided by 2 pi. That doesn't exist for arbitrary J. It can't, because J is a continuous parameter and the dimension is going to be an integer. To construct the Hilbert space, you have to quantize the parameter J, set it to preferred values at which the Hilbert space exists. Those special values correspond to the angular momentum in the real world of electrons, atoms, and molecules. It's because of the last step that the subject is called quantization. So the subject was named quantization because the parameters became quantized, and the parameters became quantized because of finding a Hilbert space realization.
Is it a matter of Hilbert structure, or it's a matter of existence of finite dimensional representation and choosing the value of the Casimir?
Well, the Hilbert structure is important, of course, because the Hilbert space norm gives probabilities. So
in physics, yes. I mean, mathematically, if I just first start formally with an associative algebra over polynomials and then study representation theory of this algebra, but without a reality condition, but just decompose this category by the values of the Casimir and then recover these integer values of this quantization condition on H bar.
Well, you'd find that special things happen at that value of H bar. That's fine. I'm stating a physicist's point of view about what quantization is. So quantization is constructing the Hilbert space that the algebra acts on. That's where physics happens. So the states of electrons, atoms, and molecules are correspond to vectors in a Hilbert space. And probabilities. Now, Gukov and I asked whether the A model in this general setup can describe quantization and not just deformation quantization. So the answer is yes, under certain conditions. So recall that in general, we're discussing a complex symplectic manifold Y. In geometric Langlands, Y is the moduli space of Higgs bundles, which we view as a real symplectic manifold with symplectic form M omega. So let's discuss Lagrangian A branes, which are the usual branes of the Fukaya category, or the most familiar A branes. They're branes supported on a Lagrangian submanifold L, a submanifold L that's Lagrangian for M omega. Now, in many of the examples important in geometric Langlands, L is actually a complex Lagrangian submanifold. That is, it's Lagrangian for omega, not just for m omega. For example, if you take a skyscraper sheaf on the dual side, which is supported on a point in the dual Higgs bundle moduli space, its dual is a Lagrangian brane supported on a fiber of the Hitchin fibration. That's a complex Lagrangian submanifold. That happened because a point in the Higgs bundle dual moduli space is hyperholomorphic. In other words, it's a sheaf that's holomorphic in each of the three complex structures of the hyperkähler manifold. So in general, a complex Lagrangian brane is dual to a sheaf that's not just holomorphic, but hyperholomorphic. And just like most holomorphic sheaves aren't hyperholomorphic, most Lagrangians are not complex Lagrangians. So in general, L won't be Lagrangian for omega, only for m omega, just as a coherent sheaf isn't in general hyperholomorphic. So Gukov and I considered the opposite case of an A brane whose support M is Lagrangian for m omega, as it must be, but is symplectic for real omega. So that's the opposite case of a complex Lagrangian brane. Complex Lagrangian means Lagrangian for m omega and also Lagrangian for real omega. We considered the case of an A brane that's Lagrangian for m omega and symplectic for real omega. Of course, the truly generic case is neither of these two, but more complicated to study as far as I know. So we argued that in this case, Hom from B to BCC represents a quantization of M with symplectic structure real omega. For example, if Y is an affine variety, then the holomorphic functions on Y, which are deformation quantized to get the algebra Hom from BCC to itself, can be regarded as analytic continuations of certain real analytic functions on M. There are enough of them to be a reasonable quantum deformed algebra of observables. And then Hom from H, which we'd find to be Hom from B to BCC, is an A module, which one can show has appropriate properties to be a quantization of M. So we argued that this should be called a quantum Hilbert space because we had a formal argument reducing the description of H to the problem of quantizing M. Now, I've actually made it a key point. What structure is needed so that Hom from B to BCC is a Hilbert space, not just a vector space? In general, if B1 and B2 are any two branes, there's a non-degenerate bilinear, not Hermitian, pairing from Hom B1, B2 times Hom B2, B1 going to C. So to get a Hermitian inner product is the same as finding an antilinear map between these two spaces. Gukov and I showed there is such an antilinear map, which I'll call theta tel, if there's an antiholomorphic map of Y to itself with M as a component of its fixed point set. So I won't explain the definition of theta tel, but I'll explain why one should expect the existence of such a tel to be the right criterion. If holomorphic functions on Y act on H and H is a Hilbert space, one will have a notion of which holomorphic functions are Hermitian. Existence of tel gives a natural notion. A holomorphic function on Y is real if it's real when restricted to M. So to go back to Jan's question, which is whether there's a natural version where you'd have all the structure of quantization but not a Hilbert space inner product. Gukov and I had that if we took M to be symplectic for real omega and Lagrangian for m omega, but do not impose this further, much stronger condition that there is an anti-holomorphic map tau with M as a component of its fixed point set. So if you do not impose this last condition, you get something with all the properties of quantization except the existence of such a Hilbert space. And we actually studied some examples like Harish-Chandra modules for SL2.
Edward, could I just ask you a question here about this inner product in relation to Chern-Simons theory?
Yes.
So Chern-Simons theory has indeed this tau here, right? Because this is multiplication by -1 in the Higgs field, I assume.
Yes.
Or actually, yeah. Or you described it in your paper. But so which inner product would you envision on the quantization of bond G?
Well, it's a fascinating example, which, as I think you know, I've grappled with on and off throughout my career. So A proper
Me
answer
too.
is way far afield and take much too long time for this lecture. That's an important example where it's strongly believed and maybe even known mathematically that there is a unitary structure that's preserved under the flat connection over Teichmüller space.
That is known, yes.
There's no explicit formula for the flat connection.
Exactly. Yeah.
Dukov and I did not have a definition in this framework of the Hermitian structure, but in our current work, Ioto and I, for your example, have discussed your example again. Unfortunately, the paper isn't quite finished, but we've discussed your example again, and we do have in that framework a definition of the inner product, but it's a definition that's not elementary to calculate. I'm pretty sure there's no explicit formula for the correct inner product in that example. So we have a new perspective on what the inner product means, but it doesn't lead to an explicit formula, I'm sorry to say.
Okay, all right.
It'll come as a surprise, a happy surprise, but still a surprise if there is anything you'd call an explicit formula. But I guess there are surprises in life.
Yeah.
So if you're given this tau, I didn't quite explain the definition of theta tau, but if you're given tau, the Hermitian product is, you take the bilinear pairing that exists in general in the A model, then use theta tau to map one space to the other, and the composition of theta tau with the bilinear product gives a Hermitian pairing. And this is a Hermitian pairing for any pair of branes that are tau invariant. It's always non-degenerate, but for general tau invariant branes, it's not positive definite. For the more specific case relevant to quantization, the best we can say is that the pairing is positive definite if you're sufficiently close to a classical limit. This is a point that we don't understand very well, I would say. So in this approach to quantization, if you're given a real symplectic manifold that you want to quantize, you have to find a complexification of M to a complex symplectic manifold Y with some appropriate properties. And then you can use the A model of Y to quantize M. That might be loosely compared to geometric quantization, which is the closest there's been to a systematic approach to quantization. In geometric quantization, to quantize M, you have to find a polarization of M, roughly a maximal set of Poisson commuting variables. Given a polarization, geometric quantization gives a recipe of quantization. So geometric quantization or quantization by branes can give good results for geometric quantization if there's a natural polarization, for quantization by branes if there's a natural choice of complexification for the problem at hand. A limitation in my paper with Gukov is we didn't understand much about how to compare brane quantization to geometric quantization. Now, Gaiotto and I looked at this in the last few months more closely as background to understanding the work of Eddinghaus, Frankel, and Kazhdan that I mentioned at the beginning. So we were able to get at least some better understanding of the relation of quantization by branes to geometric quantization in the following sense. If M has a polarization in the sense of geometric quantization and a complexification suitable for brane quantization, then under certain conditions, we showed the two methods will agree. So at least we found a criterion in which the two approaches to quantization are compatible. And this, for us, this was important because the work of Eddinghaus, Frankel, and Kazhdan was natural in geometric quantization. But to apply duality to it, we needed to know that we could understand it in brane quantization. So we worked this out as a step to making sure we could apply quantization by branes to what Eddinghaus, Frankel, and Kazhdan were doing. So all this has been by way of preparation to talk about the work of Eddinghaus, Frankel, and Kazhdan that I mentioned at the start. So they consider a Hilbert space of L2 functions, or better half densities, on the moduli space of semi-stable holomorphic G bundles over C. C is a Riemann surface. Then they construct operators in H that are related to the usual constructions of geometric Langlands, and they found interesting duality theorems and conjectures concerning the action of these operators. Now, because of the time, I'm not going to systematically state at the beginning what various theorems and conjectures were. We'll proceed with the physical setup and see what those statements might be. So in geometric quantization, we'd understand the L2 functions on the moduli space in terms of quantization of the cotangent bundle of the moduli space, which is birational to the Higgs bundle moduli space. And in an L2 theory, throwing away a set of measure zero isn't important. So we'll think of their story as the quantization of the Higgs bundle moduli space. In other words, the Hilbert space of Edinger-Franklin-Kazan is what you get if you take the Higgs bundle moduli space with its real symplectic structure, which is the imaginary part of its complex symplectic structure, and you quantize it using geometric quantization, using the fact that it's a cotangent bundle. On the other hand, if we're going to get anywhere in terms of predictions from duality, we need to understand quantization of the Higgs bundle moduli space via Branes. For this, the first step is to pick a complexification of the Higgs bundle moduli space. Now, this has a very simple and general answer. The Higgs bundle moduli space is a complex manifold, but we're viewing it as a real manifold. Any complex manifold viewed as a real manifold has a canonical complexification, namely y hat, which is the product of two copies of y, taken with opposite complex structures I and minus I. So you see, y hat has an involution that exchanges the two factors. Since we took them with opposite complex structures, this involution is anti-holomorphic. Its fixed point set is the diagonal. So we've realized y as the fixed point set of an anti-holomorphic involution of a complex manifold, which is the starting point for quantization by Branes. Now, since the complex structures on the two factors are opposite, we can take the holomorphic symplectic form to be 1/2 omega on one factor and 1/2 omega bar on the other factor, which I'll write as a 1/2 omega box plus of a 1/2 omega bar. So that's the complex symplectic structure on the product. Then the restriction of omega hat to the diagonal is real omega. In other words, y is Lagrangian for m omega and it's symplectic for real omega. So this is the situation that's appropriate for quantization by Branes. So that's the situation in which it makes sense to quantize y using a Lagrangian Brane B supported on y. Moreover, the real polarization on y that leads to the Hilbert space, studied by Edinger-Franklin-Kazan, does analytically continue to a holomorphic polarization of y hat, which is the technical condition needed to know that quantization by Branes agrees with geometric quantization. So the Hilbert space they study is indeed the one that arises in brane quantization. However, we have to ask, what are the observables in brane quantization? Let's recall Hitchin's integrable system. The Higgs bundle moduli space has a Hitchin fibration pi from the moduli space to B, where B is Cn for some n. The linear functions on B are Hitchin's commuting Hamiltonians. Classically, the global holomorphic functions on the Higgs bundle moduli space are just the pullbacks of functions on B. In other words, the algebra A0 of holomorphic functions is the algebra of polynomial functions of the Hitchin Hamiltonians. What are the quantum observables in brane quantization? Well, for brane quantization, we define the canonical coisotropic brane BCZ hat of y hat to be a product of coisotropic branes on the two factors. So the algebra that acts, since the brane is a product, the algebra that acts on the quantization is a product. It's simply A tensor A bar, where A is Hom on one factor, B is Hom, A bar is Hom on the other factor. The quantum deformed versions of A0 and A0 bar, the holomorphic and anti-holomorphic functions on Y. Moreover, for the case of the Higgs bundle moduli space, you can show that the quantum deformed rings A and A bar are still commutative. That's due to Hitchin for SL2 and to Beilinson and Drinfeld in general. The quantum deformed objects are the commuting differential operators that are the quantization of Hitchin's classical commuting Hamiltonians. So the four-dimensional gauge theory picture gives another explanation of the fact that the quantum deformed ring is still commutative, similar to the explanation I gave of the commutativity of the Hecke functors. Now, we want to understand the action of Hom from BCC hat to itself equals A tensor A bar on the Hilbert space, which was Hom from B to BCC, which in this case is just L2 of the moduli space of bundles. First of all, there's no mystery about the fact that A tensor A bar does act on L2 functions on the moduli space. That's just the statement that homomorphic and anti-homomorphic differential operators on M of G can act on functions on M of G, which are in general neither homomorphic nor anti-homomorphic. Homomorphic operators trivially commute with anti-homomorphic ones. And the
excuse me, I forgot the L2 structure is taken with respect to the Keller form, which is what?
Well, M of G has a natural Keller, has a natural Keller structure.
It's even hyper.
It's not hyperkeller. No, it's the moduli space of bundles.
Of bundles. Sorry, yeah, that's what I was confused. Yeah,
that's a natural hyperkeller. But I was cutting some corners and calling it L2 of M of G. The more natural brane quantization in general would make sense if M of G didn't have a natural Keller structure, and it naturally leads to half densities. So you could argue that the more canonical framework formulation of this is in terms of half densities on M of G, and that's what Frankel and Kazan say. However, because M of G does have a natural measure, half densities are equivalent to functions, and I was just cutting a corner to not introduce half densities. But it's better to introduce half densities and not make use of any special property of M of G here. So, homomorphic and anti-homomorphic differential operators naturally act on smooth functions, commuting with each other, and the algebras of homomorphic and anti-homomorphic differential operators are separately commutative, according to this result of Balanson and Drinfeld. But now we get a question which was addressed by Edinger, Frankel, and Kazan, and a earlier and less precise version had been discussed by Teschner. What are the joint eigenvalues of Hitchens Hamiltonians and their complex conjugates? To answer this question, we want to apply duality. Maybe I'll stop for a moment for any other questions before I go on.
Sorry, maybe I can ask you a question. So you actually worked out a flat connection, which is operating in this L2 of Mg, which is sort of the analog of what I would call the Hitchin connection, but it's sort of what I call the Hitchin-Witten connection, which is the connection that you have in this L2 bundle, the trivial bundle over Teichmüller space.
Yes.
And now, how is the compatibility between parallel transport of that connection and then these constructions here?
I'm extremely embarrassed. I haven't tried to figure that out. It's embarrassing. It's actually an excellent question. I'd better not try to say anything on the fly. The question is certainly one should ask. I don't know what to say.
Okay.
Any other questions? Well, okay. So to apply duality to this picture, we need naively to understand the duals of the three branes involved, which are the coisotropic branes on the two factors, and also the brane supported on the diagonal. Now, as I mentioned before, the coisotropic brane on one factor has a dual which is the structure sheaf of the variety of operas. That's a result of Balanson and Drinfeld, which we struggled to understand in physics language, but did eventually understand. An opera is a flat bundle whose homomorphic structure obeys a certain condition. And likewise, BCC2 is essentially the complex conjugate of that brane. So its dual is the structure sheaf of the Lagrangian submanifold that parameterizes flat bundles whose anti-homomorphic structure is an opair. But what about the brane B that's supported on the diagonal? Well, there's an unfolding trick that shows we don't have to worry about dualizing the diagonal. So remember, we're studying the A model of a product of two copies of Y. So I draw it as a theory on a two-sheeted Riemann surface. Here's one sheet, here's the second sheet. This copy is mapped to Y1, this copy is mapped to Y2. They're completely decoupled except on one boundary. At the left boundary, they're still decoupled. Each one has its own coisotropic brane. But on the right boundary, there's a brane supported on the diagonal. And the boundary condition is just that the map from this sheet to Y and the map from this sheet to Y agree on their common boundary. So if we unfold it, we just have a single sheet mapped to Y, and this particular brane has the property that nothing is happening there. So after unfolding, we can just completely forget about the brane B. And we don't have to answer the question of what his dual is, or if you like, that question has a trivial answer that follows from this unfolding trick. So in the unfolded version, there's just a single copy of the Higgs bundle moduli space, and the Hilbert space is Hom between two quasitropic branes, where BCC is the quasitropic brane I told you about, and BCC tilde is the conjugate version of BCC adapted to the opposite complex structure minus I instead of plus I on the Higgs bundle moduli space. So we just dualize BCC and BCC tilde to get L, the Lagrangian variety supported on the variety of O pairs, and the Lagrangian variety supported on the variety of conjugate O pairs. In other words, the varieties in the Higgs bundle moduli space of the dual group that parameterize flat bundles whose holomorphic or anti-holomorphic structures, respectively, are O pairs. A becomes Hom from L O pair to itself, which is just the algebra of holomorphic functions on L O pair, and A bar becomes Hom from L O pair bar to itself, which is the algebra of holomorphic functions on L O pair bar. So here I've written the dual pictures. On the left, we have the picture that leads to quantization of the quantization of Bun-G. Well, quantization of the Higgs bundle moduli space. So in other words, L2 functions on the ordinary moduli space with the action of the Hitchin holomorphic and anti-holomorphic Hitchin Hamiltonians. So if you like, the question is on the left, and the dual version on the right will enable us to answer the question. On the dual version, you have the moduli space for the dual group, and the boundary condition on the left is given by one Lagrangian submanifold. The boundary condition on the right is given by a different Lagrangian submanifold. So the spectrum of A tensor A bar is Hom in floor theory, if you like, between these two Lagrangian submanifolds. So LO pair and LO pair bar are Lagrangian branes. So this is an intersection or Hom space in a version of floor cohomology. This might be slightly confusing because the assertion that both holomorphic and anti-holomorphic O pairs are complex Lagrangian submanifolds of the same complex manifold in the same complex structure might be confusing. So the G-dual description is by a B model of the Higgs bundle moduli space in the complex structure in which G-dual parameterizes flat G-dual bundles over C. The complex structure just comes from the fact that G-dual is a complex Lie group and has nothing to do with C being a complex manifold. So for example, traces of holonomies are holomorphic functions on the Higgs bundle moduli space in this complex structure. A flat bundle has both a holomorphic and anti-holomorphic structure, both of which vary holomorphically in this complex structure. So in fact, there's a holomorphic map in this complex structure from the Higgs bundle moduli space to Bun-G of C times Bun-G of C bar, where C bar is C with opposite complex structure. And we're just taking the pullback of, a flat bundle is an O-pair holomorphically if it has a non-trivial extension, and it's an O-pair anti-holomorphically if it obeys another condition. But both of these conditions are holomorphic in the relevant complex structure. So some of you will know this definition, but I'll explain it a little bit more in a few minutes. Now, by the method I explained before using an anti-holomorphic involution tau, Hom from BCC tilde to BCC carries a Hermitian inner product, which we expect to be positive as it corresponds to the quantization of a cotangent bundle. The dual space, Hom from L O pair bar to L O pair, likewise carries a non-degenerate inner product, which is defined similarly using an anti-holomorphic involution tau dual of the dual Higgs bundle moduli space. This non-degenerate inner product can be defined for any B branes, LO pair and LO pair bar, that are exchanged by tau dual. But for generically, it will not be positive definite. Conditions that make it positive definite were formulated by Edinger, Frankel, and Kazan, who showed that these conditions are satisfied for GL1 by direct but surprisingly non-trivial computation, and for SL2 by a theorem of faultings. So consider a point X where these two Lagrangian submanifolds intersect. It corresponds to a flat bundle E that's an O pair both holomorphically and anti-holomorphically. The anti-holomorphic involution talent dual that's used to define the Hermitian structure on the G-dual side will map E to the complex conjugate flat bundle E bar, which is also an O pair both holomorphically and anti-holomorphically. If E isn't isomorphic to E bar, then they're both null vectors for the Hermitian form on Hom from L O pair bar to L O pair, which in that case is not positive definite. But duality predicts it should be positive definite, so we expect that, as conjectured by Edinger, Frankel, and Kazan, and proved in some cases, E is always isomorphic to E bar. Thus, the claim is that the flat GC bundles that are O pairs both holomorphically and anti-holomorphically are actually real. That is, their structure group reduces to a real form of G. Assuming the intersection points are all real in that sense, this Hom space is positive definite if and only if all the intersection points are always transverse. That statement is also among the results / conjectures of Edinger, Frankel, and Kazan. Note that if a flat bundle E is an O pair holomorphically and is also real, then it's also an O pair anti-holomorphically. Bundles with that property are what Edinger, Frankel, and Kazan call real O pairs. So assuming the duality is true and the Hermitian form is positive definite, the Dorian spectrum of A and A bar corresponds to real O pairs. Let me recall that according to Balanson and Drinfeld, an element X of A, first of all, is a holomorphic differential operator on bun G, and second corresponds to a holomorphic function F sub X on the variety of O pairs. Similarly, an element X prime of A bar is an anti-holomorphic differential operator on bun G, corresponds to a holomorphic function Fx prime on L O pair bar. So an intersection point P of L O pair and O pair bar determines a pair of eigenvalues of the differential operators X and X prime, namely Fx of P and Fx prime of P. So that's the proposal for the joint spectrum of Hitchin's quantized Hamiltonians. Now, Edinger, Frankel, and Kazan also introduced Hecke operators as operators on the Hilbert space H that arises in quantizing MH of G as a real symplectic manifold. I explained already that line operators of the four-dimensional gauge theory can be used to define functors on the category of Branes, or boundary conditions. Moreover, Hooft and Wilson operators correspond to dual pairs of functors on the A and B model categories. The same line operators represent operators on the quantum Hilbert space. I've tried to explain this with the following picture. So here is a boundary labeled by brane B. Parallel to it is a Hooft operator T, and we discussed it before as an operator on the category of boundary conditions, a functor on the category of boundary conditions. Now, instead of letting T run vertically, it runs horizontally from left to right. I will have to tell you what happens at the corners where T ends on B and B prime. I'll do so in a moment. But okay, so A is the old story of a line operator as a functor on the category of Branes. In B, the same line operator with some information at the corners is used to make an operator on the Hilbert space. So the idea is that a quantum state representing an element of this Hilbert space comes in at the bottom, interacts with T, goes out at the top as a new quantum state, and the transformation from the bottom to the top is the action of a linear transformation on the quantum Hilbert space. By the way, the reason physicists call the Hooft operator an operator has to do with the fact that it can be used this way to make an operator on states, rather than what mathematically is a functor on boundary conditions. Physicists would describe it a bit differently. But anyway, this middle picture is the one that motivates the terminology at Hooft operator. Now, the picture in B raises the question of what's happening at the corner where T ends on a brane B. And the point of C is to explain that the corner represents an element of Hom from B to TB. You see, here, T is parallel to B, so we have a composite boundary condition TB. Here you have a boundary condition B. So in between, you have a morphism from B to TB. And so the corner is a morphism from B to TB, and similarly, the other corner is such a morphism. So the 't Hooft operator T with the choice of these two morphisms actually is an operator on the quantum Hilbert space. And that's supposed to represent the way Edinger, Frank, and Kazan adapted the same construction that's used for Hecke functors to make Hecke operators on Hilbert spaces. Now, the argument that showed commutativity of the Hecke functors for different points, P and P prime, and any representations of the dual group, goes over immediately to show that Hecke operators used as operators likewise commute. Because they live at different points in C, they can be moved up and down past each other in this picture without singularity. So in the purely two-dimensional picture, the operators might not commute, but because they're hidden dimensions, they do commute. Moreover, as in the discussion of line operators as functors, we can set P equals P prime. Now, a similar argument shows that the Hecke operators commute with the quantized version of Hitchin's holomorphic or anti-holomorphic Hamiltonians. A two-dimensional picture makes it look like there could be a problem moving a Hamiltonian X past a Hecke operator TR of P, but in 4 dimensions, it's obvious that you can move X past T, and generically they don't meet. Finally, we can ask, what are the predictions of the duality for the eigenvalues of the Hecke operators? So to answer this, we start on the G-dual side. We're going to find the eigenvalues of a Wilson operator, WR of P. R is a representation of the dual group, and P is a point on the Riemann surface. We're going to find the eigenvalues of Wilson operators acting on Hom between the two varieties of O pairs. And then the duality will predict that the eigenvalues of the Hecke operator will be the same. Also, we'll find what kind of data is needed for the corners that make WR of P into an operator. Again, the duality will predict that the same data is needed to define the Hecke operator TR of P. Given a G-dual bundle E with connection over sigma times C and a representation R of G-dual, we form the associated bundle. Mathematicians write it this way. It's the associated bundle to the G bundle E and a representation R. It also comes with a connection. So WR of gamma for path gamma in the form manifold sigma times C is defined by parallel transport of the connection on ER along gamma. For the present application, we fix a point P in the Riemann surface and 2 points A and B on the left and right boundaries of sigma, and a path in sigma times P from A times P to B times P. So I've drawn it, a horizontal path from A times B on the right to B times B on the left. And then I'll let ER, E sub R, A times B and E sub R, B times P to be the fibers of ER at these 2 points. Then parallel transport defines for each connection a linear transformation from one fiber to the other, or equivalently an element. I prefer to state it symmetrically. So instead of calling it a linear transformation, I'll call it an element of Hom from the tensor product of one space and the dual of the other to C. So here R prime is the dual representation to R. Now, a quantum operator is going to come from something that's a complex valued function of fields, in this case connections. We don't have that yet. What we have is that for each connection we've defined a linear transformation or a linear form on a vector space, not a complex number. To get a complex valued function, we need to supply elements V and W of these two vector spaces. And then this linear transformation applied to V tensor W will be a complex valued function of connections that we can quantize to make an operator. This will be an easy operator to diagonalize and evaluate, as we'll see. To avoid unnecessary details, I'll state the following for the case that the dual group is SL2, and that R is the two-dimensional representation, which is also isomorphic to its own dual. But there's a straightforward generalization to any group and representation. In this picture, the boundary condition on the right boundary is that the dual G-dual bundle E restricted to the right boundary is an anti-holomorphic O pair. That means there's a non-split exact sequence. So here K bar is the canonical bundle of C bar. C bar is C with opposite complex structure. K bar to the 1/2 is a square root of K bar. We pick here a square root, but as noted by EF and K, the choice will cancel out in a moment. So if we pick a vector V in K bar 1/2, the fiber of K bar to the 1/2 at the point P in C, that gives the vector J bar of V in one of our fibers. Similarly, on the left boundary, the boundary condition says that E is a holomorphic O pair, implying that there's a non-split exact sequence. So we pick W in Kp to the 1/2, and that gives us J of W in the fiber on the left boundary. In other words, the corners correspond. The corners correspond to choices of V and W in K to the 1/2 and K bar to the 1/2. That gives us the information we need. The information we need to define W as a complex valued function are these corners, are these vectors V and W, to which we then apply J and J bar. So once V and W are picked, the complex value function of connections that we're going to interpret as a quantum operator is this one. So this step is trivial because in the B model, one can actually assume that the connection is pulled back from C. So that being so, the quantum operator that corresponds to the connection, there's an imprecision in this statement that I'll correct in a moment because SL2C has a non-trivial center. So I should have said the connection is pulled back from C up to an element of the center of SL2C. The reason the statement is true is that O-pair bundles are irreducible. So the only indeterminacy in this parallel transport is by the center. So up to sign, this operator is just the natural dual pairing between these two, from these two vectors in R and R prime to C. So its value at a real O pair is simply the pairing of J bar V with J of W. So it was convenient to write the formula this way in terms of V and W, but it actually only depends on V tensor W. And V tensor W is in a real line bundle with no dependence on a choice of spin structure, as was observed by EF and K. So the duality then predicts that also on the right-hand side, the definition of T of P as an operator requires these corners V and W in K bar to the 1/2 and K to the 1/2. That's true as shown by EF and K using an algebra geometric formula. And then the duality further predicts that the eigenvalues of the resulting operator are what we found on the G-dual side, namely this, for all the possible real O pairs. From a lecture by Edward Frankel, I realized that in this statement, I was omitting to take into account the center of SL2C. So because of the center, parallel transport from left to right is uniquely determined up to sign. So actually the eigenvalues are these same expressions with both signs occurring. Thank you. So to summarize, just to summarize, I gave an overview at the beginning of the gauge theory approach to geometric Langlands, and then what you have to do with those ingredients in general to describe quantization. And then we talked about the work of Eddinghoff, Frankel, and Kazhdan, where I tried to explain the physical picture. And I explained to you what some of the mathematical statements were in the course of trying to explain how you would understand them physically. I think that's about as well as I can explain the material for today. So I'll turn it over for questions.
Yeah, so other questions?
I do have a question, but it's rather about generalization. So as far as I understand, you essentially use the fact that moduli of Higgs bundles are birational to T star of band G, and so you use this L2 structure or whatever half densities on band G.
Yeah.
But from the point of view of, I think, like brain quantization, what's going on? So you have just a Hitchin map, which means that you have a base, which is a moduli space of spectral curves on some symplectic surface. In your case, it's a cotangent bundle to C. And then you consider, say, for smooth curves, you consider line bundles. So like this abelian varieties, which are fibers in the Hitchin system.
Yeah.
So the question is, what happened if you replace your symplectic surface, which is T star, of the curve C by something else like C star square or elliptic curve product C star or the complement in P2 to the cubic, which means that you still have a notion of a spectral curve. You still consider, say, mathematically like torsion-free rank 1 shifts supported on those curves. So you have an analog of the Hitchin map of the Hitchin integrable system, but it's not the cotangent bundle. There is no, it's not these moduli spaces. They are not cotangent bundles of anything. So how much will survive? You can still talk about brain quantization, whatever this means, but there is no projection to any base.
Well, I'll only be able to see something useful if there's a quantum field theory construction. And I need to think much more slowly about some of the examples you mentioned. It would be worth discussing them with David, I think, who might be better in some of the examples than I am. One example, one generalization I do know is that instead of, this is sort of in the spirit also of Jürgen's question. Well, sorry, I'm not sure which slide I'm looking for even, but instead of discussing just L2 functions on this bungee, we could look at L2 sections of the power of a line bundle over it. And there's a similar quantum field theory setup that leads to that. But the duality gives a different kind of answer. So for example, if you take the first power of the line bundle, I think you get something which is dual to itself. So you learn interesting things from the duality, but you don't get this answer in terms. See, part of the beauty of the story of Edinger, Fraenkel, and Kajan is that you get an answer in terms of classical geometry, the intersections of the two varieties of O pairs. Anyway, well, I don't know, broadly, I don't know the answer to your questions, Jan. All I can say is that as a physicist, to say something interesting, you'd want a quantum field theory setup, and then you might be able to say something interesting. It would really being able to say something interesting would probably depend on having some dualities that apply to the situation. And if they existed, what they would say might be different in different cases. But I'm giving you a rather uninformative general answer, I'm afraid.
Okay, so it's a question about quantum field theory interpretation of the setup, which I just mentioned. Okay, yeah, all right.
Well, do you want to, okay, you could tell me just one case, in case I can say anything about it.
Yeah, okay, like C star square, C star cross C star. It's as close to the cotangent bundle to the curve as possible. You still have a projection on one of the products.
Oh, sorry. So instead of looking at a curve in the cotangent bundle, you want to look at a curve in?
It's not a curve, it's curve is very specific, it's C star, it's just punctured line. It's C star, and instead of the cotangent fiber, I have another C star, like product of two copies of C star. It's a like complex torus of dimension 2. All right, so then I have this notion of spectral curve, which is just a complex curve inside, I mean, of this symplectic surface. And you can consider, you can and construct an analog of the of the modular of Higgs bundles. You just look for something like rank 1
Oh, I
bundle.
understood you. You just are discussing C star times C star instead of the cotangent bundle for Riemann surface.
Yeah, for example, yeah.
That's certainly a nice example physically because it's self-mirror, actually. The fact that, well, there are facts that I'm sure you probably know much better than I do that are related to the fact that it's self-mirror. You get the two algebras, e to the x and e to the p, and e to the 2 pi x over h bar or
Yeah,
something.
my impression was that if you look for the analog of your story, then first you will have a quantization parameter q in the story, and for the conjugate picture you have this modular conjugate, like
Yes.
yeah, all right, and
That's
then
right.
like these algebras A and A bar, it will be like sort of, you know, this Fadeev quantum dialogue.
Yes.
Yeah.
Yeah.
But
I don't understand it. I agree with everything you're saying, although I don't understand the example very well.
yeah, me too. So yeah, I have some understanding, but without real kind of this L2.
But somehow the quantization should lead to the functional identity that Fadeev's quantum dialog satisfies, right? If you can quantize the classical
I mean,
analog.
this can be worked out even mathematically, I believe, by many people, by Fadeev himself, by Goncharov, Fok and Goncharov.
What do you mean by working? I don't know much about it, but I'm not satisfied with the proofs, which look like they involve computations. The explanation I would want is an a priori explanation of computation, where brane quantization was intrinsically defined and can be computed in any of the 5 polarizations whose comparisons involve this quantum algorithm. I don't really feel I understand that explanation, but that's the one I would have aimed for.
But either a trigonometric version of an oper, like it's like Q connections. Instead of connection with an infinitesimal shift like d over dx, you have a Q connection where the function f of x goes to f of qx. You have kind of your step is quantized. You have this Q, but what's analog of the opera, I don't know.
I don't know, but I want to say that my understanding is that this example is actually dual to itself, and that's the reason that the two algebras exist. It's dual to itself with Q exchanged by the conjugate Q. And so the analog of functions in O pairs is just the conjugate algebra, I believe. Or at least that's my first answer.
Actually, yeah, it can be.
I recommend discussing the example with David, actually.
Okay. All right. Thank you.
Sure. Thanks for the question.
Could I maybe continue, but in a slightly different direction, namely sort of the quantum transformers direction? So yes. if you turn on K and have K, I mean L to the K, then we no longer have commuting operators, right? And we have these quantum Hamiltonians that both you looked at and Hitchin looked at in the early days. Yes. How do they fit into this picture here?
Well, it's too far afield to give a proper answer. Right? It's a great question. David and I were actually discussing it the last few days, but it's a little bit too far afield to properly answer now. So the setup can be applied. So, okay. As you were basically saying, you take the Higgs bundle moduli space, and then in one of its complex structures, it has an anti-holomorphic involution that leaves fixed the ordinary moduli space. So it's the right setup to discuss quantization of the Higgs bundle moduli space in that language. There are a few details you need that I didn't have time for in the lecture, but anyway, it is the right setup. So you can discuss it in that language, and you can even predict in that language that the connection has to exist. But whether in that language you can recover any known description of the connection, I don't know. We haven't gotten that far. It would be nice, it would be great to do it that way. I have a question for you, if you don't mind. I'm going to ask you a question about your questions. So, well, the trouble is I'd like to explain it in a way that everybody online understands. not just the two of us. So what we're discussing is, first, if you fix a complex structure on a two-manifold, then you have the moduli space of semi-stable bundles. It has this determinate line bundle, and you can make a Hilbert space, which is the space of sections of the kth power of the determinate line bundle. Then, as you vary a point in Teichenmayer space, that you get a vector bundle of a Teichenmayer space whose fiber is that bundle. And Hitchin and Del Pedro Axelrod and Jorgen and other people have analyzed this flat connection, which actually in Gina Zero goes back to Konishnik and Zamolodchikov. I'm forgetting them. So Jorgen was asking about understanding that flat connection in this language. There's something I don't know about it, but I feel it might be known. So first of all, this bundle has a Hermitian structure, which you also asked about. And the flat connection is unitary relative to that Hermitian structure.
Yeah.
That's definitely predicted by physics. First of all, I don't even know if that's a math theorem. Is
it
that
is.
a math
theorem? Yes, it is. There is a, it follows from my work with Kenji Ueno that it exists to combine with Laszlo's work. So the thing is that we already know that there is a well-defined unitary structure on the TQ of T from the quantum group point of view, Recitikhin to Reyev.
Yes.
And then because we now know that it is isomorphic projectively canonically to the quantizational moduli space of bundles, we can port the unitary structure over and it will be parallel with respect to the Hitchin connection.
I see. So roughly speaking, you're not directly constructing the unitary structure in the quantization, but you know that its global monodromies are unitary because of comparing to Reshetikin and Tureyev, and then you deduce the unitarity.
Right.
So,
yes, and I can say a little bit more about the inner product. I actually know that it can be written of the form, the pointwise inner product of sections times a function that depends on k times the Liouville measure associated to the Goldman symplectic form. And I know some, sorry? Mm-hmm.
That's great. And the physics does predict that formula. So
okay. Yeah, and then I can prove that the asymptotics as k goes to infinity, the leading term is e to the minus a half times the Ricci potential on this moduli space.
Oh, really?
And then it has an asymptotic expansion 1 over k, and I don't know explicit formula for the next terms.
Okay, so according to physicists, this function is the partition function of the WCW model of SL2 mod SU2 at level k. And one could, you're telling me what, comparing the two statements makes a prediction for what should be the classical action of the dominant solution of that model. Since you have an answer, hopefully it can be compared. Doing so involves things I don't really know, so I can't try to say anything offhand, except to say that there would be a physics prediction.
I see. That would be very interesting.
But regardless, I have a question to ask you about it. And I do not know whether the answer to this question is known by either physicists or mathematicians. I also do not know. I do not remember. This interpretation was suggested to me by someone 30 years ago, and I can't remember who, unfortunately, so I can't attribute it. But because there's a Hermitian structure on this bundle, you could define a connection that just comes from that Hermitian structure. Is that actually the flat connection?
Well, it is up to projective equivalence.
Yeah. Okay.
So that's there is a, yeah, that's true up to projective equivalence.
Well, I would say I didn't define things precisely enough to have made a more precise statement than that.
And there is, I know, a way to actually correct it in such a way that you really have a differential operator that gives you the connection that is the Chern connection.
By Chern connection, you mean the connection that comes
that is compatible with the Hermitian structure and the holomorphic structure in the bundle.
Okay. Okay, that's good. Offline, maybe you could send me some references.
Yeah, sure.
Okay. There's something I'm curious about, which might have been answered in the physics literature a long time ago, if so at a time when I wasn't following it, which is, as I told you, there's a formal physics answer for what your function would be, the exponential of this, the partition function, rather, of this non-compact WCW model.
Mm-hmm.
Then there's a question whether the flat connection is what you're calling the Chern connection.
Yeah.
The first statement might imply yes to the second question.
And I think it somehow has to be, because it's sort of compatible with the holomorphic structure almost by definition, because we want the 0-1 part of the connection to be the holomorphic structure in the bundle.
Okay.
And then it should be a Hermitian connection because it should preserve the inner product.
Okay. Well. Okay. I want to think about it more often, but I think that's believable. Okay. Well. Anyway, the context of my lecture, all I can say though is that it makes sense to look at these questions in the framework I was talking about, but we haven't gotten very far in doing so.
Okay. Yeah, that's very interesting. Thank you. Any more questions?
Can I perhaps ask a much lower level question, if that's possible?
Sure.
So at some point you explained why the T, sort of those lines between the boundaries, could be seen as an operator.
Yeah.
And that visually that made a lot of sense to me, because you could see it as a boundary inside the interior. But you also explicated that obviously this was a 2D picture of what was really a 4D story.
Yes.
And in the 4D case, it's not as obvious to me that that line would be a boundary for the interior to itself. Could you?
Well, the Hecke functor modifies the boundary only at a point. For example, the way mathematicians say it is that.
I see.
Okay, you're right in asking this question. So the boundary is the timeline that was drawn times a Riemann surface. The boundary is really a 3 manifold. And I did not say that the boundary condition has to be homogeneous on the 3 manifold. It does have to be homogeneous in the time direction, because we're studying the theory as a 2-dimensional topological field theory, but we can do what we want on the Riemann surface. So in our category of boundary conditions, a boundary condition isn't required to be homogeneous on the Riemann surface. And the functors I was talking about modify the boundary conditions just at a point on the Riemann surface times anywhere in the timeline. If I might compare to what mathematicians do, there are Hecke functors that modify a bundle only at a point. And the dual of Hecke functor is usually stated mathematically without explicitly formalizing it as a Wilson functor that also acts at a point. But since the Hecke functor only acts at a point, the Wilson operator acts also at a point. So anyway, you're right in asking the question, but these boundary conditions are not required to be homogeneous on C.
Thank you.
Any more questions? So if you don't mind, maybe I could also ask, does this new approach via brane quantization shed any light on defining the boundary state vector in Schoen-Simons theory, say for a handle body that describes Lagrangian, you know, in flat connections, which is a complex submanifold in the complexified Lie group?
Not that I know, actually. That question is actually, okay. Sorry to talk about all my other papers, but that question is a little bit closer to my work on Covenant homology than, which used the same ingredients as in this lecture in a different way. Okay. This is work of about 7, 8 years ago. But even though it's closer to your question, I still doubt that I learned anything new about your question. Other physicists working in that direction may have, but I better not try to say anything right now.
I was simply wondering if one could create a sort of ideal of operators that kind of annihilates the state, and it's sort of the unique vector that's that is in common joint kernel.
Okay. Oh, okay, sorry. Yes, sorry. Okay, that makes sense, right? Something like that makes sense. But, okay, well, let me just say what is true and try not to make too big claims. So if you have a 3 manifold whose boundary is the Riemann surface, I'm not sure if, the camera's here, so when I try to pantomime with my hands, I don't know if you're seeing it or not.
No, see, it's fine, it's fine.
Okay. Right. So if you have a 3 manifold whose boundary is the Riemann surface, that actually defines a brane in this theory, as you perhaps intuitively imagined. And it's actually a brane of type BAA. So it's a complex Lagrangian brane. And you're correct that deformation quantization of that brane will give, well, it'll involve an ideal or okay, a module for the quantum deformed ring of functions. I'm not sure what else to say about how close that is to your question, but it might be. I think I'm better off stopping here while I've only said true things. Although I can tell you one other thing, which is that Eddinghoff, Frankel, and Kashtan have also done some work on maybe I should say it in my language instead of trying to say it exactly the way they do. I explained a two-sided picture where you have a Riemann surface times an interval times time, and you have the coisotropic brane here and its conjugate coisotropic brane here. You could also, if you have a Riemann surface that's defined over R, which means it has an anti-holomorphic involution, divide the whole picture by an involution that exchanges the two sides. And then you get a one-sided case, meaning that you have a Riemann surface that's the boundary of a three-manifold. That'll be a very special and very simple three-manifold. So it's a very extremely special case of your question, really. But that particular case of your question is related to something in geometric Langlands where we can make contact with something they do, although not, well, the case that's easy for us isn't the case they've looked at. So what we've actually done as of now can't quite be compared to what they've actually done. But in principle, yes. Anyway, that's a case of your question, which is, I think, possibly too simple a three-manifold for your interests.
Well, no, I'm not sure. I mean, maybe one could get handle bodies this way by considering the interval across the surface and dividing out by such an involution. Maybe.
If the involution doesn't act freely, you can perhaps get a handle body. I might say that if it doesn't act freely, I also don't understand the duality predictions.
Yeah, okay.
So we only understand the case where it acts freely, and then the three-manifold won't be a handle body.
Yeah.
But we'd like to understand the case that don't act freely. It's just harder.
I see. Yeah.
But anyway, okay. For general three-manifolds, the construction makes perfect sense and gives branes, but they won't be related in an obvious way to geometric Langlands, at least not right away.
Okay. And is that because they're not sort of half Lagrangian and half symplectic as the ones you're treating, or?
Sort of, yes, roughly.
They're more generic.
That's as well as I can say it quickly.
Yeah. Okay. Excellent. Thank you.
Sure.
Any more questions? No? Maybe not. So thank you very much, Edward, for an excellent lecture. Super interesting. Thank you.
Thank you for the invitation, Jürgen. And
you're welcome. Our pleasure.
Okay.
Yeah. Okay. Well, thank you very much.
Bye-bye.
Okay. Thanks. Bye-bye.